Hello, I'm Hamta Setmani. I'm gonna introduce our design time tool. At this stage, we assume that we did some profiling activity of AI application in a way that some performance models are available. Now I present SPACE4AI-D design time tool, which general goal is the design space exploration of the design alternative. So the goal is given the set of candidate resources, identify the resources with minimum cost to be deployed in the computing continuum in a way that costs are minimized and taking into account some technology and performance constraints that are set by the designer. This is challenging because usually the computing continuum are heterogeneous and these are based on technology that are growing fast, and actually some optimal decision today might be suboptimal in a few months. So in the current practice, an AI designer has to test the deployment of AI application component under different settings by considering alternative devices. For example, alternative flavor of virtual machines, and with AI application, this combinatorial design space is even increased because of the fact that AI applications can be partitioned. Since this process is very time consuming, the number of candidate solutions that can be tested are limited and only a suboptimal solution can be identified. Vice versa, with SPACE4AI-D, the AI architect has just identified which is the set of candidate resource to be deployed in computing continuum, and then the tool will identify automatically the optimal deployment of minimum cost. Additionally, for deep learning components, multiple candidate partitioning will be also identified, and this will be leveraged at runtime to cope with workload fluctuations. The final deployment is checked by the application manager that then can automate the deployment of application by relying on infrastructure manager. This is the workflow related to the tool. We start from a YAML system description. This system YAML description is shared among the multiple tools that are used within AI Sprint. So here the application architect specifies the candidate resources, then this system YAML file is transferred to a specific parser to be transformed to the input file format of the different tool. So SPACE4AI-D will implement a parser to translate the system YAML into a JSON file, while for example for PyComs we developed a parser to transform XML file that are used for configuration of PyComs runtime. Then in this JSON file, the application architect needs to add the description of the control flow of the components and has to specify the performance demand for the resources or to associate to the component with the machine learning performance models. And then finally the optimal YAML file is identified and will be deployed automatically by relying on the infrastructure manager. In our demo, we are considering another application called mask detection application that is shown in this picture. This application is run according to the function as a service paradigm, includes two main components. The first component, given the video which is uploaded in the system, this component selects some frames and blur the faces for privacy reasons. Then the second component is in charge of identifying the red and green brackets that we were showing on previous figure. The first component actually in our setup can be run alternatively on Raspberry Pi with or without an accelerator, while the second component, mask detector, since it's more computing intensive, can run in the design space exploration in the Raspberry Pi with accelerator or in two different VM flavors. The information of candidate resources is provided in the YAML file. The YAML file includes two main sections, network domain and containers. Network domain has some information about the network which connects computational layers together, like access delay and bandwidth. Each network domain includes at least two computational layers, and each computational layer includes at least one candidate resource. In this use case, computational layer 1 has Raspberry Pi with or without accelerator in the edge side, and computational layer 2 has two different type of VMs in the private cloud. The container section consists of AI application components. In this use case, component 1 includes Blurryface that can be run only on computational layer 1, while container 2 consists of mask detector component that can be run either in computational layer 1 or computational layer 2. This information is not enough for a SPACE4AI-D tool. Moreover, the tool needs JSON file as an input, so by a parser, the YAML file is converted to a JSON file. This is the JSON input file of the tool. The only things that are missing from YAML file and code parsing shown in red are a dependency graph and performance that needs to be completed by the designer. Performance denotes some machine learning models to predict the component execution time. We also support queuing model to compute the component execution time. Now I'm gonna show how to run the tool by command line. The tool is written in Python 3. The script name is main.py. We use switch-s to give the path of input JSON file, and we use switch-c to give the path of configuration file that includes the iteration number that random greedy needs to be run. And we use switch-v to set the verbosity level to print logs. Now it's printing some messages about loading configuration file and when a solution is improved by random greedy. Now I show the YAML output file. In the output file in computational layer section, only the selected resources are shown. A Raspberry Pi without accelerator is the selected resource in computational layer 1, and VM type 1 is the selected resource in computational layer 2. In the container section, the placement of each component is mentioned. Given the compatibility and performance constraint, component 1 is placed on computational layer 1 and component 2 is placed on computational layer 2. That is the optimal placement that the tool could find. This was a toy application just for demo purpose. To evaluate our proposed random greedy approach utilized by the tool, we considered a large-scale use case of identifying wind turbine blade damage that is inspired by one of use cases in AI Sprint, including 5 components in a pipeline, such that component 1 can go only to computational layer 1, while component 2 and 3 can be placed on computational layers 2, 3, and 4. And finally, component 4 and 5 can go to computational layer 3 and 4. We considered a local constraint on component 5 and a global constraints on a path includes components 1 to 4. The incoming load in our experiment varied between 0.1 and 1 request per second. To evaluate our method, we compare random greedy with Hyperopt, which is a Python library based on Bayesian optimization, and also we define a hybrid method. In this method, first we run random greedy for some iterations and feed the results to Hyperopt to see if Hyperopt can improve random greedy results. To quantitatively evaluate the different approaches, we define the percentage gain denotes as the cost ratio, where other method cost can denote the cost of a Hyperopt or hybrid method. These figures show the cost comparison under light constraints for 1000 and 5000 iterations. The first figure shows that random greedy costs are up to 10% lower than those obtained by HyperOpt, while the second below shows the comparison with hybrid method, and it can improve random greedy only up to 1%. This slide indicates the result under strict constraints. Random greedy always finds feasible solution if it is possible, while disconnected point in the first figure shows that HyperOpt cannot find any feasible solution in 20% of scenarios. On the other hand, the second figure indicates that a hybrid method never improved random greedy for 5000 iterations. Moreover, as it is reported in the third figure, even if we run random greedy for 5000 iterations, the required time is at least one order of magnitude lower than the other methods running for 1000 iterations. To evaluate the scalability of our approach, we consider 4 different scenarios at different scales, and we reported the average achieved by considering 10 random instances for each scenario. The result shows that our approach can obtain significant improvement, such that maximum execution time for a random greedy is about 4 minutes for largest scale scenario with 5000 iterations. Thanks for your attention.